1.18? All right. Anyone else get the same thing? Okay, a couple dots. All right, so I know what the average time is. The mass of this, oh no, it's just the block. We could go through some fancy ways of doing it, but it's going to turn out the mass doesn't matter. So I'm going to just make it easy on myself and just say it's 1 kilogram. All right, so we're going to assume the mass is 1 kilogram. The reason why the mass doesn't matter is that it's all proportional. If the mass increases, the triangle still looks the same, it just expands. This angle here was about 30 degrees. So if it's 1 kilogram, what is the weight of the object? How would you find the weight? Did somebody just mumble it? All of you have done this on the lab. Or most of you. Depends on if you haven't done labs or not. Given the mass, how do you find the weight? What's the formula? Look it up.
Can you move it 3 decimal points?
Sure. I was actually just to settle for the formula, or did you already do the calculation? So what's the formula for weight? I didn't quite hear that, Jennifer.
It says mass times gravitational force. To get the weight, is that not right?
If it says mass times gravitational force, weight is a gravitational force. So if it says that, you're on the not a good site.
Mass times acceleration.
Of
That thing up there.
no, mass. It's mass times the acceleration due to gravity, or gravitational acceleration.
No.
mg. W equals mg. So the mass, 1 kilogram. G,
It said 9.798.
that's what it is for Winston-Salem. Sure, let's go for that, 9.798. 9.798. And so my weight of my object is 9.798 newtons. So I now know this value right here. This is, since this was my weight, this is 9.798 newtons. This is a right triangle here. This is my normal force. This is friction plus my net. So if I multiply this, and the reason why I'm not going to get into, but if I multiply this times the cosine of 30 degrees, so on your calculator it would be 9.798 times the cosine of 30 degrees. You get 8.66, 8.64. If someone would be kind enough.
I don't know, there's
If you've got a negative, are you in radians?
I got 1.5.
Cosine of 30 degrees. No, it won't be 1.5 something. You did this.
Times the 9.798.
Yeah. Something's off. Oh. You're in radians, not degrees. So to get 1.5 something, your calculator is in radians. Pardon? That's the cosine of 30, not cosine of 9.7.
Would it be 29.5?
Say it again?
29.5?
No, it's gotta be less than 9.798.
I got 8.49.
That makes some sense. 8.49?
Yeah.
So my normal force is 8.49 newtons. This side over here, the total length of this side, and again, not going into it, into y, but it would be this times the sine of 30 degrees. This would be 9.798 times the sine of 30 degrees, which is 4.8. 99. So let's figure this out here. All right, so it's side notes, probably should not be doing this example, but we've gotten this far. So I apologize, but I still want to finish it. I need closure. All right, so we have the time. We know how far it slid. It slid 1 meter. So if I have time, how far it went, what is the acceleration? This is not a problem we've really done. We know the initial velocity is 0, but how do you actually solve it? Well, in chapter 3, Hewitt gives a big clue to it. He talks about, in chapter 3, there's a problem where you have an object and you drop it, and he talks about how far it travels in a certain amount of time. So so what Hewitt has, putting in my notation, 1/2 gt squared. This is specifically for an object that starts at rest and is then released and it falls. However, it's very close to another formula. So let me just write this is starts at rest and falls. But this formula also works if we make it slightly more general, that the displacement is equal to 1/2 a t squared. And this is true if it starts at rest. It doesn't necessarily have to be falling. So I know the time, 1.18 seconds. I know the displacement. I just solve for a. Once I have a, I can figure out what this net force is. I know what the total distance here is of the triangle. I subtract that, and what I'm left with is friction. The more in doing this, the more I'm thinking, man, this is just not 1/10. But again, so I got 1/2 times a times 1.18 squared. So 1.18 squared is 1.39 times 1/2. .6962 times A. There's my math problem. I divide by the .6962, and so my acceleration is 1 over .6962. It's about 1.5 something. Someone's about to tell me.
So one divided by
1 divided by that .6962. 1.44 meters per second squared. All right, so I now know the acceleration. I know the total force is equal to mass times acceleration. So my total force is going to be my 1 kilogram mass times that number just there. So my net force is, just said it, 1.44 is equal to my 1 kilogram put 10 mass times 1.44 meters per second squared. So my total force, the total net force, 1.44 newtons. This whole side is 4.899 newtons, so just subtract them. And that tells me what the friction is. And like I said, do this longhand. 3.459. That's equal to my friction, which is equal to my kinetic coefficient times the normal force, which we found to be that. So we have 3.459 equals mu sub k times 8.49. And we end up with a mu sub k of somewhere around 0.4. So this is newtons, that's newtons. Probably more importantly, well, one, this is the general process that you go through. The only difference between this and the official ones is better timing devices. The surfaces would be, you would not probably mix the surfaces of string and iron. You'd have very precise measurements of distance. So, what are the units of my coefficient over there? What should the units be? So the question to ask yourself is, what did I divide by what in order to get that number? Let's see if I can write that a little bit more clearly. All right, so we had 3.459 newtons equals my coefficient times 8.49. It's 8.49 newtons.
what, 4 newtons?
No, not 0.4 newtons.
The mu,
The units of mu. That's what I'm trying to figure out. Or want you to figure out.
K newtons?
No. How do you get mu by itself? How do you solve for mu? What do you divide by?
8.49.
Newtons. So you divide both sides by 8.49 newtons. So that part, that's the calculator piece, that you get somewhere around 0.4. What are the units? Pardon?
Is that the, were you asking what was the answer for that?
Oh, you got 0.45?
2.45.
2.45?
Wait.
Something can't be right there. I'm only concerned with the units at this point.
Did it cancel out?
Yes. There are no units, it's unitless. It's just a number. If you had said newtons per Newton, I would have accepted that too. All right, so here's some problems. One, we're using reflexes for that. It's not necessarily a smooth surface, but the coefficient of static friction should not be less than the coefficient of kinetic friction. I have done labs like this for years, and it is rare that you actually get what you'd expect, that mu sub k is less than mu sub s. However, it does not make sense if it were. It does not make sense that it would be that way. So, because for mu sub s we had 0.185, for mu sub k we have somewhere around 0.4. Yeah, I haven't figured out why those experiments never quite work. But again, I wanted to take you through the process. I've done that. No doubt the silence was just, you were struck with, again, the awesomeness of physics. Or it's the class of introverts, which I can appreciate. It is a long marathon, but have a wonderful day. As a teaser for next week, Newton's third law of motion. And we'll wrap it up. We'll wrap up 4 and 5 next week.